Today's session is about phase plane analysis. Phase plane analysis is one of the earliest methods developed for the study of linear and nonlinear second order systems. The idea behind this technique is to analyze the motion trajectories of the states of the system for various initial conditions in a state space. Let us now see what a state space is. Generally speaking, for an nth order system, a state space is a space defined with n states as its coordinates. In the figure you can see a three-dimensional space defined with x1, x2 and x3 as its coordinates. You can also see a two-dimensional plane defined with x1 and x2 as its coordinates. When it comes down to a second order system, the space can be treated as a plane where x1 and x2 are the coordinates of the system. Thus, a state space for a higher order system reduces to a plane. We call this plane a phase plane. This graphical representation of the states was developed by a French mathematician Henri Poincare. Even higher order systems can be reduced to second order systems and motion trajectories can be visualized to see what goes on in the system. Let us now consider the state model representation of a second order system. X dot is equal to 0, 1, minus 2, minus 3 into x. Its solution can be written as x of t is equal to Laplace inverse of Si minus A inverse into x of 0. We can see that the solution depends on x of 0. Now let us assume we have two initial conditions. One is 1, 0 and another is 0, 1. For an initial condition x of 0 equal to 0, 1, we get the solution as e raised to minus 2t plus e raised to minus t, 2 e raised to minus 2t minus e raised to minus t. Whereas if the initial condition is 1, 0, you can see that the solution is minus e raised to minus 2t plus 2 e raised to minus t and 2 e raised to minus 2t minus 2 e raised to minus t. This will be x1 of t and this is x2 of t. For the second case, this is x1 of t and this is x2 of t. Here we have explicitly found the equations for x1 and x2 for two different initial conditions. With the knowledge of this equation, we can very well plot the states for various values of time. For example, if you have the initial condition as 0, 1, then the phase trajectory would be like this. And if the initial condition is 1, 0, the phase trajectory would be like this. You can also see that without this x1 of t and x2 of t equations, we can find these trajectories by different methods. This will be explained in the upcoming videos. Here we discuss the different system descriptions depending upon the nature of the system. We have different types of second order systems. A general second order system description would be x1 dot is equal to f1, which is a function of time x1, x2 and u of t, where x1 and x2 are the states of the system and u of t is the forcing function. Similarly, x2 dot would be another function f2 of time x1, x2 and u of t. Suppose that the input function is not present, that is a forcing function is not present. Then these equations would reduce to x1 dot is equal to f1 of t x1 x2 and f2 of t x1 x2. This means that the input function is not present. Now we consider another class of second order systems wherein the time function is not explicitly present in the x1 dot and x2 dot equations. That is, x1 dot would be f1 x1 comma x2 and x2 dot would be f2 x1 comma x2. Such systems are called autonomous systems. If the function f1 and f2 are linear, we call it as linear autonomous system, and if the function f2 and f1 are non-linear functions, we call non-linear autonomous systems. Given are some examples of linear autonomous systems and non-linear autonomous systems. Linear autonomous systems will be of the form x dot is equal to ax, whereas non-linear autonomous system would be of the form x dot is equal to f of x. We can't write a constant A matrix in this case. So, a non-autonomous system would be something of the form x1 dot is equal to 5tx1 plus 2x2 and x2 dot is equal to, maybe I can take it as 10x1 plus 2tx2. In this case, since t value is explicitly seen in the equations, we can see that they are not autonomous systems. We have seen what a phase plane is. It is a plane describing the states of the system. If you have a second order system, we have x1 and x2 as the coordinates. But a major class of second order systems are described in the form y double dot minus f of y comma y dot is equal to 0. For example, a differential equation of the form y double dot minus 7y dot minus 3y equal to 0 is familiar to you. In this case, in order to form the state model, what we normally do is we select y, that is the output, as one of the state variables and its derivative as the other state variable. In that case, the state model can be obtained as x1 dot is equal to x2 and x2 dot is equal to 3x1 plus 7x2. The phase plane is formed with y and y dot because x1 is y and x2 is y dot. Traditionally, you can see that these states were used for system descriptions or motion descriptions. Phase plane was developed for plotting y and y dot. But we can very well plot x1 and x2, which are the two states of the system, in a phase plane. The motion trajectories of x1 and x2 are generally called state trajectories. In particular, if you use y and y dot, we call it as phase trajectories. For different initial conditions, we can draw different phase trajectories. So, the family of phase trajectories with different initial conditions form something called phase portrait. Generally speaking, we can see that phase trajectories do not cross each other. But there are certain exceptions for this, which will be discussed later. This will give you a better picture of the phase plane method. We have seen that for a second order system which is autonomous in nature, we can write x1 dot as f1 of x1 comma x2 and x2 dot is equal to f2 of x1 comma x2. Let us, for example, consider these two equations for x1 of t and x2 of t. Let us assume that these solutions are obtained for an initial condition x1 is equal to 1 and x2 is equal to minus 6. We can substitute different values of time and obtain the values of x1 and x2. And for every time, we can see that a pair x1 comma x2 is obtained. So, with the initial condition 1 minus 6, that is this point, I have drawn the state trajectories or the phase trajectories. We can see that if you put another set of initial conditions, we can get another equation for x1 of t and x2 of t, and let us assume that that phase trajectory is given by this green color. That shows that for different initial conditions, we can draw different phase trajectories, and the nature of the phase trajectory will be totally depending upon the behavior of the system. In short, we can say that these phase trajectories depend on the eigenvalues of the system, the details of which will be discussed in the upcoming videos. Thank you.